Hi, my name's Tyler. So many of you know Matt and a lot of the people who at Bloomberg who probably contributed on the RGW side. I herald from our compute side. I lead our compute infrastructure team, and I'm here today to talk to you about designing and tuning for all-flash our Ceph RBD storage. So we do a lot of openStack at Bloomberg, and I'm excited to hear that Squid was focused on performance. We've found some things in the block side that I don't know that the community's necessarily known about yet, so I'm excited to share them with you today. So designing for scale, I do want to talk a little bit just about our infrastructure and some of the choices that we've made, and I don't want to spend too much time on it because it's not necessarily too Cephy, but I think it's something cool to talk about. If you're interested, come talk to me more later. So at Bloomberg, we've been doing OpenStack and Ceph since about 2013. And our design goals, our personal design goals, are very dense compute. We pack up to 22 NVMe's per server, very deep storage. And our first foray into OpenStack, when we started doing this, that we've since kind of adapted for, is if you go to an OpenStack conference, you hear a lot of talk about challenges that people have when they start having thousands and thousands of VMs, whether it's some issues with Neutron or ARP storms or stretched L2 domains, whatever it is. So we re-architected our network to basically be completely based on L3. So sometimes you have to think about how are people consuming Ceph. The Ceph, your Ceph cluster maybe have hundreds or thousands of hosts, but you may have tens of thousands or more of containers. And all those in a block world, you have your Rados clients talking directly to your Ceph servers. It's not necessarily just the gateways. And so what we do is we can basically have these servers announce their IPs into the fabric, and then the fabric just knows the shortest path to where the VMs are. So this kind of networking fabric, this kind of design, alongside all-flash Ceph storage, has allowed us to do some really cool maintenance activities. So when we upgraded to Quincy from Octopus, we actually do an OS upgrade and a whole bunch of other things. So we just decided to actually leverage the fabric and the flash storage, and we actually totally formatted every drive. We zapped everything, we rebuilt all of it, we backfilled all of it, and no customer impact. So all of those changes to things like I think default block size, or maybe somebody in Rados will correct me, and think around like Pacific, we can pick all those changes up by constantly destroying and rebuilding our OSDs. And there's a whole bunch of ancillary benefits. So if you're kind of on the network side and you have to move some equipment in your data center, you have to drop VLANs, you have to re-IP things. But in an L3 fabric, you just move things around. And BGP learns the quickest route to that host. So it's really great from not only a performance perspective, but actually maintaining things as well, and especially for containers. But as I said, this is a Ceph conference. So we'll start talking about some of the performance issues that we've run into and how we solve them, and some of the interesting things I've learned that I have not seen the community talking about yet. So this is a story on swapping. So we spent a lot of time with the L3 networking idea in the OpenStack world, and Ceph was kind of put off to the side for a little bit while we were focusing on this. And we finally got confident in that L3 design, and so we finally got some kind of attention to give to Ceph. And at the time, we were due for big OS upgrade. We were also running Octopus. This was 2022, so it was a little old. We're going to Quincy. And we started by looking at our Ceph cluster. It was good timing because we were starting to see swap on our all-flash systems, and it was even sometimes getting to like laggy PGs. So first thing we did is just drop the memory target on some of the OSDs to buy us some time. But even though we dropped the memory target by 25%, there was still some swap, which was weird, right? Like, we still had plenty of memory capacity before we dropped it, and then we dropped it and we're still swapping, even though like our swappiness was set very low. So we wanted to understand what happened, and eventually we did figure it out. And the answer was not to turn off swap. It was actually something else that we found out that ended up spilling into like a whole bunch of performance improvements. So our journey began with just basically building some benchmarking. We're lucky. We have a very nice lab cluster with a couple hundred OSDs. They're all flash, the 2 by 25 gig networking. This lab cluster is not indicative of our production clusters. I just want to point that out. So any figures you see are just things in the lab. And so what we did is set up a bunch of repeatable benchmarks, a whole bunch of different block sizes, queue sizes. We even did some IOP limited testing and just measured tail latencies and things like that to get an idea of where we were, so when we make changes, we can understand what they're actually doing. And when we started out, we had a big problem. We would just rerun the benchmark, and like write performance would swing as much as 10%. So if my variance is 10%, I can't tell if any change is actually helping, right? Because it's just such a wide amount. Unless I figure out to make something like 30% faster, which I probably won't, unless something's really misconfigured. So the first step for us was actually just to fix the variance, or understand why there's so much variance. And I think this graph here is just network bandwidth of when we were slamming the cluster with writes. And we expected it to kind of level off, but even that was very jittery. So the first thing that's almost funny, we found out we forgot to disable scrubs. So at like 5 o'clock, the benchmarks, results were all different than other times. It's like, yeah, don't forget to enable scrubs. However, somebody on the team told me something interesting. They said you might not want to leave no scrub set indefinitely, because apparently there may be some kind of deferred scrubbing that will happen eventually if you just never scrub. Eventually on reads, it will get upset. I don't know if that's true or not, but it's something to kind of consider. You might not want to just also leave no scrub set. So the problem wasn't scrubbing. We didn't turn off swap. What we did start to see when we started looking at this is that this is a host during some of the benchmarks, and this stood out. Some cores are running really hot, and we started profiling what's going on with those cores versus the others, and it was the NIC driver. Its RSS processing was occurring on all those cores. And so what we did is look at the NIC driver, and there was an option to change the RSS queues from the cores running on the local Numa node where the NIC was to the threads. So we changed that, and sure enough, it spanned out to the threads. So it kind of opened a whole bunch more questions like, where is the kernel running Ceph? Where is memory being assigned? Because we're running 22 NVMe's in this host. Of course, a Ceph OSD process is has all kinds of things inside of it. It's not just 22 processes. So we started looking at things like NumaStat, and this was the tip of the iceberg. When we started seeing, basically, node 3 is where the NIC is running. And if you see Numa foreign is 0. So what that means is Numa foreign is when I want to allocate memory on my node, but I couldn't. I had to go to somebody else's. So you basically have processes like grabbing memory from all their Numa nodes because they're so, there's no room. And so you see node 1, 2, and 3 are basically all grabbing memory from node 3. So there's some really weird like kernel scheduling stuff going on here. And started looking at more stats like the actual zone statistics, and it was like, eureka. What's happening is that some zones were starving from memory. So there might have been available memory capacity if you looked at memory holistically, but within those zones, they were starving. So disabling swap was the wrong thing to do. It will stop swap, but the kernel's still going to react to memory pressure in those zones. It's still going to page out. It's still going to do lots of other things. So not only was this Numa thing that we found out, it's like not only did we start looking at it and realizing it's a memory balancing problem, there's actually a huge performance advantage that you can have with Numa as well. So not all architectures are this extreme, but this one's very interesting. So if you look at, you take a cache line and you bounce it between 2 cores in one of these chiplets, it's like 20 to 30 nanosecond of memory latency. If you go to the adjacent chiplet, it goes all the way up to 80 or 90. So it's like 3, 4 times. If you go across the die, it's a little more. And so what's interesting is you think, maybe you've been doing 1P Ceph systems because you think, well, I don't want to have the Numa penalty. But the thing is even though you have a 2P system versus 1P system, that's a 5x latency. But if you look at the green, 20 to 30 nanoseconds, versus a chiplet on all the way on the other side of the die, you're paying just about as much, the magnitude difference is just as much from die to die as it is from package to package. And what's even more telling, missed a slide there. What's even more telling is that if you look at that die, there's 8 Numa nodes there. By default, vendors will only show you 4. You actually have to go into the BIOS and change a little setting to get to show you all 8. So probably if you didn't go to your BIOS and change something, you're in the yellow zone. And you could be green if you had the chance to optimize it. And why a lot of people don't do it is because the kernel has to be aware. So what we did is we wrote a small systemd shim. You don't need to do this. You could just basically, instead of doing it templated, you could just basically write some files in there. And what we have a tool doing is dynamically probing the system, seeing how many OSDs there are, and then making a decision about where to put those OSDs on which Numa node. So we're actually doing this kind of pinning ourselves ahead of time, and we're putting those OSDs closest to the NVMe's where the OSD is actually hosting a storage for. And this helps us to actually leverage the benefits of these architectures. And so this system on the bottom was actually, its uptime is far, far, far greater than the one before. But you see, as soon as we did that, now our Numa 4 is actually much lower. Numa hits are much higher. We're actually hitting that, using our memory local nodes. And this really started to show up in big ways. When we did our upgrade from Octopus to Quincy, we halved our context switching. It went in half because we weren't having things bounce around all the time and fight for memory and grabbing into each other and RSS queues waking up Ceph and forcing all these context switches. And this resulted in a huge drop in variance. And it allowed us to actually increase the performance and understand what each change was doing to our system. So if you haven't done Numa yet, I recommend it. And we were so confident that this was the fix, we actually increased the memory target again, even though we were swapping before. And since then, haven't swapped a single byte. So do understand what changes you're making. Don't make reactionary decisions. If you haven't looked at Numa yet, you should, especially if you have a very dense Ceph cluster, and especially if you're doing blocks, something very latency intensive. It'd be great for something like C star. And do look at your BIOS settings before you do this. Different architectures are going to show different degrees of memory latency between those chiplets or dies, depending on the computer architecture at hand. But most computer architectures, you have to go and enable sub-Numa to get these kind of benefits. And so what kind of realized maybe we know some things that the community doesn't. There was a Ceph.io post in 2024, and this made me feel terrible when I saw it. Because I had opened a case up in 2020 with this same exact issue. So if you saw it in certain vendors' packages, I apologize. We should have done a better job there and actually gotten that up all the way upstream. I will take responsibility for that, and hopefully some of the things today, like the Numa balance that we show you, we can actually get back into the Ceph tree. So Numa balancing is one thing. The biggest challenge that we face with Ceph today is that performance issues can be very intermittent. Sometimes they're here today and they're gone tomorrow. So when you have a block storage cluster, you're really only as fast as your slowest OSD. And we have some really extreme cases of this. And our customers basically let us know. If we make Ceph 30% faster, as we did when we went to Quincy, our IOPS went up by 30% in a lot of clusters. They didn't really notice. But when there's blocked I/O, they very much notice. So your worst case is what your customers really care about. And so a lot of our optimizations are understanding when things go wrong, why they went wrong, and how we can mitigate them. But before we pick on Ceph, and this goes back to don't change things unless you really understand what's going on, there's a bunch of white papers online. They're well-intended, and they actually work very well, or not very well, but they do improve things for old Ceph releases. So these white papers for all-flash storage will tell you, use these RocksDB settings. It's usually they want you to bump the number of background compactions, some other things that make sense. So I'm ashamed to say we had this in there, or some kind of variant of it, and then when we went to Quincy, performance was terrible. It was awful. And it was some really weird things. We would start an OSD, and it would take 10 minutes before the OSD went back up. It was taking so long that Ceph was actually marking it out. And eventually, what we found is that there's a PR. So if you are not on Quincy yet, make sure you didn't mess with this setting. There's a PR that actually changed the max WAL size, which is a good thing. Because if you don't do this, you have 100 gigabyte WALs per OSD. And when it goes to compact or you go to restart that OSD, it just starts spilling, and your cluster performance just tanks. So don't just take settings online or something you saw without measuring it and being able to reflect on what those changes are doing. Because this change was insidious. It would sometimes take like 1 to 2 days before it would manifest, because that WAL would actually have to fill up before it started compacting. This one was really interesting. So, again, we're running block clusters. They're very latency sensitive. And the kernel has a I/O timeout parameter. It's 30 seconds for NVMe devices by default. Seems kind of long, but maybe like NVMe over fabrics, I don't know. And we have this very once in a blue moon problem where the NVMe just stops sending interrupts, it seems. Like you'll get an I/O request and no interrupt for it. And eventually the kernel, after 30 seconds, is like, did you do that thing? And the NVMe is like, yeah, I got it. Well, the thing is by default, it's in direct conflict with Ceph, which uses a 150-second suicide timer. So if the NVMe keeps responding every 30 seconds, it will never shut down. It'll just keep going. So if you have an all-flash Ceph cluster, you do probably want to change these settings and make sure they're in alignment, so that when the NVMe drive does start acting up, or if it does, Ceph will just kick it out instead of trying to hold on to it and having a lot of I/O latency. And then the last one, and probably the more interesting one that we've seen. So I've looked at Ceph flame graphs from time to time. And usually it's not this extreme, but almost always, for us anyways, iSCSI CRC32 is at the top. Yeah, and in this case, it was taking 20% of the process's time when I finally got around to finding it. It wasn't always like this. And in fact, first, flame graph. So to kind of show you the relative, it is really taking 20% of the time. It's dominating the thread pool over there. It's more than basically any other Ceph process. And if you look at the thread pool in particular, it was 43% of the thread pool's time. And so I was trying to understand what's going on. I ran it again, and it was gone. It was back at 3%. And the issue with the cluster that I was trying to understand, it didn't happen again for a very long time. And so I went back to our telemetry, and I wanted to understand what was the load average, or what was the CPU load on this process. And you could almost see it when it went into this CRC panic mode. And so taking away things like this, or being able to identify this, is really what your customers care about. They like, when you solve these kinds of problems, understand why these kinds of things are happening. This is a lot more important to them than just increasing average performance. So I started looking at this, and I found out something that seemed kind of cool. Ceph uses this CRC function by default. There's actually 3 of them in the source tree. There's an 00, an 01, and an 02. 02 requires some AVX 512 or something, I think. But 01, it only requires SSE 4.1. It basically does some vectorized folding of the message buffer. And so I ran some micro benchmarks to see, is there just a faster CRC function hiding about? And it turns out, definitely yes. It's 25 to 40% faster just by changing 00 to 01. You do have to have the CPU support. This is not in the tree, but something I literally just saw the other day. I do want to be honest, though. It's really weird. one of the newer vendors, it doesn't seem to make any improvement. But then on my laptop, it got like 45% faster, and it was extremely repeatable. But even if it doesn't benefit, the vectorized version pollutes the L1 data cache a lot less. Its lookup table is much smaller when it has to fold that into a constant. So it still is probably beneficial. So it's just some takeaways. Don't change ceph.conf unless you understand what the change is. Don't be like us. Set your suicide timeout to something less than 30 seconds, or raise your IO timeout if you're using NVMe's, or at least consider it, because if you do get into that situation where the NVMe just keeps timing out, it will never suicide. And maybe we can change the default CRC32 implementation. So there's already basically some feature flags or some statements in Ceph that will detect SSE 4.1 at runtime. So this would be a very low-hanging fruit. And make sure you have time series. Thank you.